So I think it's going to be a good conversation. Just upfront, let me tell you that I'm hoping to keep it just scientific and not to enter to that much of a political conversation. Unfortunately, coronavirus became a political topic, which should have never been. But we are just trying to essentially pass that level and focus on what science tells us about where we are with this pandemic. And amazingly, everything these days are good news coming, and I think you will be pleased with the information provided. Everybody, no matter what walk of life, everybody is extremely tired of this thing. Everybody in the whole world wants it to disappear. It's just not only from health perspective, but from economic perspective, from emotional perspective. It has been really tolling on us. All right. I think we have waited enough for people like me who are always late, and I would be one of them if I was not the speaker. But let's, if you agree, let's get going. And I'm going to start sharing the screen. And again, you guys, if you wanted to interrupt me when I'm presenting, that's fine. If there was something really burning or I said something really wrong, please do interrupt me. Otherwise, I will try to be short and then we can have a conversation afterwards, but just your choice, whatever you wanted to do. All right, okay. So first of all, I need to a little bit qualify myself because as you guys all know, there are a lot of people saying a lot of stuff about coronavirus and just some of them is amazing. So my name is Faris Farasadi. I have a PhD degree in virology and molecular oncology. So I am a cancer scientist who works on viruses to make them good viruses that kill the tumors. So I had training in both areas, oncology, molecular oncology and virology. The virus that I worked on and I work on today is herpes simplex virus, the virus that causes cold sore. And I am at the Kansas City VA Medical Center. I have the pleasure and honor of working there and serving our veterans. So from the perspective of my educational background, let me admit this person and we're gonna go. This is the Kansas City VA Medical Center on Missouri side. It's a fantastic hospital. The research ranking of it is really high. And we just had a significant renovation. This area that you can see by my cursor, which is about 5-6 floors, is all research laboratories. People work on different things. I work on cancer, and recently I'm starting a project on coronavirus. And then people work on ophthalmologic diseases, kidney diseases, cardiovascular diseases, both laboratory research and clinical trials. And I did my PharmD degree in Tabriz Medical Sciences University in Iran. That's where I was born. And then I did my PhD in University of Calgary. This is University of Calgary in Alberta, Canada, next to Canadian Rockies. I never forget how thrilling it was to be able to jump in a car and go to Canadian Rockies for the weekend. Although I never ever learned how to ski, but you know, I enjoyed the mountains. But after that, I had the pleasure of joining a lab for my postdoctoral fellowship at Harvard Medical School and Massachusetts General Hospital. And now let's see, that's the Mass General. The lab that I joined was the lab that for the first time injected herpes inside human brain to kill brain tumors. And that was a significantly scary thought at that time, but our group under leadership of Dr. Robert Martuza accomplished that. And now that's being pursued in phase 3 clinical trials as treatment for brain tumors. So the point I'm trying to make is that not all viruses are bad. We have very friendly viruses, including the first virus which is approved in the pharmacies for targeting melanoma, which is also a herpes virus. So the science, we are at the level that this, through the science, we can dictate what viruses are going to do for us. This guy, coronavirus, caught us by surprise, but we will take care of that too. My training ended at Mayo Clinic, Rochester, and then I was a faculty at University of Minnesota Medical School, and then University of Kansas until 2015. And in 2015, I had the pleasure of joining Kansas City VA Medical Center. Okay, now what is a virus? Again, if my presentation is too simple for a group of you, I apologize, but we are trying to make it non-technical as much as we can. And we have to essentially provide some basic biology definitions. So the viruses are microscopic parasites, essentially. And they are called as the border between the life and death. Amazingly, nothing is like a virus. Outside a living cell, a virus is just a chemical molecule, just a chemical molecule. And inside a living cell, it comes to life with one mission and only one mission: produce progeny virus, produce more and more viruses. Sometimes that replication, that production of progeny virus kills the cells, and sometimes it doesn't. The virus stays in some sort of good relationship with the cell and just enslaves the cell to produce progeny virus and doesn't kill it. The one that kills, we call them lytic viruses. And the other ones essentially do not cause cell lysis. So from that perspective, is an absolutely amazing thing. And probably those of you who have read the history of medicine know that there was a long time until scientists could prove there is a virus. The virus exists, simply because they would purify it and it would lose life, and they couldn't convince anybody that this was the thing which caused the disease, because at that point it was a chemical, like an acid or a base. And the first group of viruses that human beings could find were viruses in plants, essentially. So, okay. Now let's move forward, hopefully. Okay. Viruses come in different shapes. They all look funny. But these funny things can cause significant issues, and we have been through them. And if you go through human history, I think viral diseases have killed a lot of human beings, more than many other diseases. So helical, polyhedral, spherical, complex, there are other shapes. And your guy, coronavirus here, is actually a spherical virus. So do you guys see my cursor as I am pointing to it? The shape looks like this. Herpes virus looks more like this one, the orange one. So let's go next one. As I said, in our lab, we work on oncolytic viruses. These are viruses that attack, these are tumor cells here, that attack tumor cells and blow them up. And they do not target normal cells. When they see a normal cell, essentially they can't do anything to it, because we have changed their genome to be like that. And there is like 10 versions of them in phase 3 human trials, and one version already approved, and the rest of them are coming. Breast cancer, brain tumors, hepatocellular carcinoma. My lab works right now on liver cancer, priority, because a lot of our veterans come down with liver cancer, unfortunately. And we also work on brain tumors and hopefully breast cancer soon. Okay, now about coronavirus. Not good viruses, the bad virus, the bad guy. So it's rather a simple structure. It's rather a simple structure. And these flags that you see on the surface of it, which right now I think they say coronavirus did two things. First of all, everybody has a clean corner in their house because of Zoom meetings, and everybody became a part-time virologist. So these flags, these red flags called spike proteins, are the ones that cause disease, essentially, because they attach the virus to your cell. If the virus, if you breed it and cannot attach to your cells, remember, if it doesn't enter your cell, it's not going to do anything. It's just a chemical that you will clear out. And a lot of viruses do enter our body, but they can't attach to our cells. Therefore, they don't cause any problem. Some viruses might actually do attach to our cells, but they don't do any harm to it. The ones like coronavirus are the ones that their replication, as they come in, they replicate in the cells, they enslave everything in the cell, and that causes harm to the cell. So if you cut that, inside of it is a piece of RNA. So outside of it, this outer crust is all protein and lipids. Inside of it is, majority of it is a RNA. What is RNA? RNA is the commanding material that the virus, genes of the virus, that the virus needs to bring to inside your cell. Therefore, it could tell your cell to look at this command and make me more progeny virus, make the proteins that I need to make the progeny virus. So the command center is inside, no different than your cell. The cell in your body has a bunch of proteins that they do the work, but the command center is inside an area of the cell called nucleus, and the command material is there. And if you essentially want to do anything, the command should come from inside the nucleus. Okay, so one more time, two things we're going to talk about a lot here. One is this RNA inside, and this spike protein, which are these molecules right here. We are right now, anything that is going to be injected to you is on the basis of disrupting this structure in a way that it can't bind. This spike structure, in the functionality of it is that it would not let the spike find its receptors on your cells. So let's see what else we have here. Now, this is when the virus attaches to cells, this is how it looks like. That is this liquid here, liquid looking thing is the surface of the cell. And then we have these receptors on the surface, and we didn't make these receptors in our cells for this virus to come and attach to it, but unfortunately, it uses it. It's called ACE receptor, ACE inhibitor receptor. So what happens is that the virus, these spike proteins, which are green here, their 3D structure, their shape is in good relationship with this receptor, binds to it and goes inside. If we were all mice, it would have never happened because mice doesn't have this receptor, this kind of receptor on its cells. But we human beings, unfortunately, do. Not unfortunately, because this receptor has its own normal function, but in the context of coronavirus infection. Now, okay, so why do we say that the masks work? It's just simple physics. There is nothing amazing about it. This is the size of not a virus. I'm going to show you how the size of a virus is. This is a virus in a droplet, because when we sneeze, when we cough, these viruses are in a globe of water. So this is the size of it. And then look at the fabric and look at the paper that is used in the surgical mask. So you can see that the majority of these droplets cannot go through the fabric. There are holes that they can do. That's why fabric masks, as fashionable as they might be, and as more pleasant that they might be, they are actually less effective than the regular surgical masks, the blue masks. Because this one on the right is a blue mask. And then N95 is an advanced version, which it could be much smaller. So surgical masks or N95 are mostly in this category, and they have much smaller holes. And also electrostatically, they are charged, they can absorb material. So it's just a simple concept. During the next couple of months until we get the vaccination, I encourage you to, if you are using a fabric mask, please also consider using at least a surgical mask. At least consider that if you are going to be in proximity of people. That would increase your assurance of not getting infected. Okay, now let's see how big is a coronavirus. As you can see, here is the human hair, and then here you got the fine beach sand, and here is a grain of salt, and then it just goes on. Like the most probably relatable are a grain of sand and a grain of salt. and then all the way different cells. And then look at here, this globe is the virus inside the respiratory droplet. And we are very lucky that the virus, the way it is, it comes out in the droplets, because compare the size of the droplet right here with the size of the naked virus, this red one here, 0.1 to 0.5 micrometer for a naked virus, and 5 to 10 micrometer for the droplet containing the virus. You are looking at a good tenfold increase in size, which helps these masks to catch it. And that's a good thing, essentially. So there are obviously viruses smaller or bigger than coronavirus. Okay, this is coronavirus under a very powerful microscope as it's going and attaching itself to your cells in 3D. That's the number of virus versus the surface of the cell. And if you cut it on the real electron microscope, this is how this gosh darn thing looks like. You could see these spikes in under electron microscope, these dark areas sticking out. And this is stained. It doesn't have that much of a color. There's appropriate technique done to make a contrast to it. So that's what we are talking about. It's real, it's there, it's small, but we can protect ourselves. That's all good things. Okay, now let's take a look at this video. And again, some of this material I show you are a little bit old, but it's also interesting to know we thought that we are not going to get any single shot of the vaccine until March 2021. And thanks God, we are in January and millions of Americans have received the vaccine. A fraction, perhaps not even 1%, but still we are on that. We are ahead of the trajectory. So let's take a look at this together and then I'll continue.
This is SARS-CoV-2. It belongs to the family of coronaviruses named for the crown-like spikes on their surfaces. SARS-CoV-2 can cause COVID-19, a contagious viral infection that attacks primarily your throat and lungs. What actually happens in your body when you contract the coronavirus? What exactly causes your body to develop pneumonia? And how would a vaccine work? The coronavirus must infect living cells in order to reproduce.
Oops. My apologies. My apologies.
This is SARS-CoV-2. It belongs to the family of coronaviruses named for the crown-like spikes on their surfaces. SARS-CoV-2 can cause COVID-19, a contagious viral infection that attacks primarily your throat and lungs. What actually happens in your body when you contract the coronavirus? What exactly causes your body to develop pneumonia? And how would a vaccine work? The coronavirus must infect living cells in order to reproduce. Let's have a closer look. Inside the virus, genetic material contains the information to make more copies of itself. A protein shell provides a hard protective enclosure for the genetic material as the virus travels between the people it infects. An outer envelope allows the virus to infect cells by merging with the cell's outer membrane. Projecting from the envelope are spikes of protein molecules. Both a typical influenza virus and the new coronavirus, they're spikes like a key to get inside a cell in your body, where it takes over the cell's internal machinery, repurposing it to build the components of new viruses. When an infected person talks, coughs, or sneezes, droplets carrying the virus may land in your mouth or nose and then move into your lungs. Once inside your body, the virus comes in contact with cells in your throat, nose, or lungs. One spike on the virus inserts into a receptor molecule on your healthy cell membrane like a key in a lock. This action allows the virus to get inside your cell. A typical flu virus would travel inside a sac made from your cell membrane to your cell's nucleus that houses all its genetic material. The coronavirus, on the other hand, doesn't need to enter the host cell nucleus. It can directly access parts of the host cell called ribosomes. Ribosomes use genetic information from the virus to make viral proteins, such as the spikes on the virus's surface. A packaging structure in your cell then carries the spikes in vesicles, which merge with your cell's outer layer, the cell membrane. All the parts needed to create a new virus gather just beneath your cell's membrane. Then, a new virus begins to bud off from the cell's membrane. Now, with the virus spreading in your body, how can you develop pneumonia symptoms? For this, we'll have to look into your lungs. Each lung has separate sections called lobes. Normally, as you breathe, air moves freely through your trachea or windpipe, then through large tubes called bronchi, through smaller tubes called bronchioles, and finally into tiny sacs called alveoli. Your airways and alveoli are flexible, springy. When you breathe in, each air sac inflates like a small balloon. And when you exhale, the sacs deflate. Small blood vessels called capillaries surround your alveoli. Oxygen from the air you breathe passes into your capillaries. Carbon dioxide from your body passes out of your capillaries into your alveoli so that your lungs can get rid of it when you exhale. Your airways catch most germs in the mucus that lines your trachea, bronchi, and bronchioles. In a healthy body, hair-like cilia lining the tubes constantly push the mucus and germs out of your airways, where you might expel them by coughing. Normally, cells of your immune system attack viruses and germs that make it past your mucus and cilia and enter your alveoli. However, if your immune system is weakened, like in the case of a coronavirus infection, the virus can overwhelm your immune cells, and your bronchioles and alveoli become inflamed as your immune system attacks the multiplying viruses. The inflammation can cause your alveoli to fill with fluid, making it difficult for your body to get the oxygen it needs. You could develop lobar pneumonia, where one lobe of your lungs is affected, or you could have bronchopneumonia that affects many areas of both lungs. Pneumonia may cause difficulty breathing, chest pain, coughing, fever and chills, confusion, headache, muscle pain, and fatigue. It can also lead to more serious complications. Respiratory failure occurs when your breathing becomes so difficult that you need a machine called a ventilator to help you breathe. These are the machines that save lives and that medical device companies currently ramp up production for. Whether you would develop these symptoms depends on a lot of factors, such as your age and whether you already have an existing condition. While this all sounds scary, the push to develop a coronavirus vaccine is moving at high speed. Studies of other coronaviruses led most researchers to assume that people who have recovered from a SARS-CoV-2 infection could be protected from reinfection for a period of time. But that assumption needs to be backed by empirical evidence, and some studies suggest otherwise. There are several different approaches for a potential vaccine against the coronavirus. The basic idea is that you would get a shot that contains faint versions of the virus. The vaccine would expose your body to a version of the virus that is too weak to cause infection, but just strong enough to stimulate an immune response. Within a few weeks, cells in your immune system would make markers called antibodies, which would be specific for only the coronavirus, or specifically its spike protein. Antibodies then attach to the virus and prevent it from attaching to your cells. Your immune system then responds to signals from the antibodies by consuming and destroying the clumps of viruses. If you then catch the real virus at a later stage, your body would recognize it and destroy it. In other words, your immune system is now primed. Collecting evidence on whether this will be possible, safe, and effective is part of what's taking researchers so long to develop a vaccine. It's a race against time to develop a vaccine amid a pandemic. Each step in vaccine development usually takes months, if not years. An Ebola vaccine broke records by being ready in 5 years. The hope here is to develop one for the new coronavirus in a record-breaking 12 to 18 months. While all of this will take time, stay home if you can to protect the most vulnerable. And don't forget to wash your hands for at least 20 seconds and as often as possible. This video was a collaboration between Nucleus Medical Media and the What If channel, where we usually dive into hypothetical scenarios.
All right, so we are back. Okay, so essentially what you saw there, first of all, was that, this video was, I think, in the middle of last year, but we did scientists and, they did it much faster than what we thought. The reason was that they didn't go the traditional route. They went to a new way of doing things, which is much faster, although we knew about that technology, which is called RNA technology. But this time there was an urgency at a global level. The resources, the financial resources became available and they could just push it really fast. So one conclusion after this pandemic, with the grace of God, is over, in my humble eyes, is that we should never cut the budget for science. We should never diminish the capacity of our fantastic scientific machinery in our universities, in our pharmaceutical industry, by cutting the budget on them. That would come back and haunt us at some point. I think that's a lesson that I don't see a lot of conversation about it, but it's absolutely true. The science brought us the treatment for prostate cancer, for breast cancer, and now is bringing us defense against coronavirus. So we should all support efforts to invest appropriate resources in scientific research. So I'm going to repeat just very briefly, as the video mentioned, the SARS-CoV virus enters your airways and then it attaches to your cells. And when it attaches to your cells, the rest of it is, very obvious for a virus. It has commanding material, as I mentioned. It injects it inside the cell, and the cell starts making everything that it needs to multiply thousandfolds and new viruses. And then these new viruses come out of the cell and they hurt the cell. They destroy the cell. The immunity then is going to pick up on them and try to activate our defense system to go and hunt both the infected cells and the virus. But if it gets overwhelmed, then it's not a good story. Number one. Number two is that because it attacks the infected cell as well, it can damage your organs, as we see in case of respiratory infections. So our immune system has a number of cells that help us defend ourselves against viruses and cancer. The same ideas exist. A foreigner, either a virus or a cell which is now cancerous, the immunity goes after it. We get the disease because the immunity cannot completely perform its job. If our immunity could completely be successful, we didn't have anything to worry about, so to speak. So macrophages, lymphocytes, T lymphocytes, you will hear these names. You don't need to focus on that. Basically, this is a schematic presentation. This cell called APC picks up the microphone and alerts everybody else that there is a foreigner, enemy, essentially. And then all of these systems become activated to go after that foreign enemy and get rid of it. But these cells, APC cells, first need to alert the immune system. And now you're going to see how they made a vaccine which helps these APC cells in their job against the coronavirus. Okay, now let's finish our biology lessons with one very easy concept. The DNA inside your cells, inside the nucleus, inside the, wherever DNA exists, needs to become RNA. And then this RNA, which is a different version of the information material, would essentially dictate the algorithm and dictate the recipe, the cooking recipe for making protein. And the proteins do everything in your body. The proteins form your cells, form your tissues, form your organs, everything like that. But the recipe to make them comes from, in our cells, comes from DNA that becomes RNA, and then RNA becomes protein. In the coronavirus, there is no DNA. There is RNA And then when the virus comes inside, the RNA is going to dictate our machinery inside our cells to make the proteins of the virus. One more time. This is also important because later on, when I'm going to demystify some of the myths, I need you to remember this. DNA is inside the nucleus. Our cell, this is a human cell. Inside the nucleus, there is DNA. DNA makes RNA. RNA then comes outside inside in an area, this yellow area called cytoplasm, okay? Called cytoplasm. It doesn't go back for majority of the situations. So RNA gets made and then comes outside in this cytoplasm. Here, the factory for making proteins exists, and you saw the 3D projection of it. This factory reads the RNA, which is out here, and makes a protein. Okay, it's another simple concept. DNA makes RNA, RNA comes outside of the nucleus, goes to the factory and makes protein. Okay, now different vaccines that, well, the only ones which are approved in United States right now is new versions of the vaccines, RNA vaccines. But the AstraZeneca vaccine, which is more of a older technology, is also, I believe it's coming for approval. These are different types. The first type that I would like to attract your attention, the vaccine material is the commanding information, DNA or RNA, which is the Pfizer and the Moderna vaccine. Both of them are RNA indeed. And there are other vaccines which have been made which are based on DNA. The second type is actually a pseudovirus that they made. So it's an harmless virus that they made which contains your vaccine. Why did they make this? Because then this virus, like a Trojan horse, can go and attach to your cell and send the appropriate message for immunity inside your cell. And we know that the virus is harmless. That's what my lab does. My lab pursues this strategy. And then there are other versions of the vaccines which are being, for example, pursued by Novavax. They are making the proteins that your immunity needs to see to become active against the virus. And they are being pursued in the research, or in case of Sinopharm and Sinovac, they are essentially making an inactive or dead virus that, again, alerts your immunity because your immunity can still see it. So when the live infectious virus comes in, your immunity is going to defend you. So as you can see, all of these vaccines, their job is to alert your immunity against the real enemy, but in a way that they don't hurt your body or they don't cause too much adverse reaction. But having this said, when you talk about 320 million people like United States, when you talk about Earth with billions of people, it is possible and very logical that some people would have certain reactions and they would get certain side effects. We have seen that through the last 200 years of medical history with any innovation in medicine, in advanced medicine. So it doesn't mean that you should never hear anybody getting sick from a virus. That has never been the case and will not be the case for coronavirus. But this safety is going to be significantly under a microscope, under challenge, and a vaccine is not going to be approved until the safety is stamped with high confidence. Okay, now the two vaccines that we have from Moderna and Pfizer are RNA viruses. Now let's take another look at it. What happens? Okay, the RNA virus gets injected to your arm, and this RNA virus, this RNA vaccine is the message to make the spike protein. And you remember the spike protein on the surface of the virus. So the RNA is the message to make the spike protein. Inside your body, your cells will make this spike protein. The spike by itself is just a protein. It's not going to harm you. It's not an infectious particle. It's just a protein. But once they make it, your immunity is going to react to it and become aware of it. So as you can see, cells such as T cells and a load of antibodies are going to be produced against the spike protein. And then the next time when the real virus comes in, which has spike proteins on it, your cells are not going to be sleepy. They're going to be waiting for it, your immunity, because they are familiar with the spike protein. And they attack it, and they don't let that virus to attach to your cells. As you can see here, the antibodies, these shapes here, they are going to essentially cover the virus, and they don't let it to come and attach to your cells. And T cells are going to go after the virus and any infected cells possible. So that's what happens with an RNA virus. Remember, the outstanding technology of RNA vaccines is being deployed for us right now, but we have known about it for a long time. Let's take a quick look at this. This one is a shorter video, but I think you would like that.
COVID-19 vaccines being developed aim to produce immunity to the SARS-CoV-2 virus by stimulating an immune response to an antigen, usually the characteristic spike protein found on the surface of the virus. Some traditional vaccines achieve this by modifying the virus to weaken or disable it, so that when introduced to the body, an immune response can be generated to the antigen, without the virus causing disease. When the immune system comes into contact with the weakened virus, its defenses, such as antibodies and T cells, attack the virus or infected cells. In the process, specialized memory cells take note of the specific antigen and prime the immune system to produce cells and antibodies that will quickly target these proteins. So the next time that person is exposed to the same virus, the immune system is ready to fight it off. Instead of using the whole virus, another way to trigger immunity involves using just fragments of it, like the spike proteins. These subunit vaccines have the advantage of being relatively easy and cheap to produce, and are incapable of causing disease because these fragments are not able to infect host cells. However, they are less likely to be recognized by immune cells aimed at attacking infected cells, which means they may trigger a weaker immune response. Because of this, subunit vaccines often include chemical agents called adjuvants, which are designed to stimulate a stronger immune response, and booster shots may also be required. Not all vaccines are designed to introduce antigens to the body. Some work by using cells in a patient's body to produce the antigens themselves. Examples include viral vector vaccines and mRNA vaccines. In both cases, the goal...
So this one merits a lot of attention because that's what you are getting right now if you go and had a shot.
...is to get a short fragment of genetic code taken from the target pathogen, in this case the SARS-CoV-2 virus that causes COVID-19, into the patient's cells. By hijacking the cellular mechanisms, these kinds of vaccines mimic the way viruses normally reproduce during natural infection. But rather than creating copies of the virus, the cells only produce large amounts of antigen that then usually trigger a strong immune response.
Okay, so you saw that instead of either making the protein, sending it, or a viral vector, now we could just send the RNA. RNA goes inside and produces a level of immunity. So mRNA vaccines are not new, as I mentioned. They have been used in cancer research, even vaccination trials against rabies and cytomegalovirus. And the production of them is fast and less problematic than the regular technology that we have been using for developing viral-based vaccines. And the issue, one of the issues is that when you make these RNAs, they have to be kept at cold temperature. Although they are doing research, and as you know, the Pfizer needs to be kept at around -100 degrees. The BioNTech vaccine does not need to be kept that cold. It's still cold temperature, but not that much. And this essentially has a problem with, may not be a problem in the United States that much, but in developing countries, some other parts of the world, it provides a logistic nightmare because access to -80 freezers or, you know, the resources for keeping the virus cold is much less than developed countries. And we are not going to be out of this pandemic in a meaningful way until there is a level of, you know, protection for the whole globe. We are in it really in real terms this time. We are in it all together. But they are working on stabilizing the next generations of these viruses in a way that they don't need to be kept in that much of a cold temperature. And then the other viruses which are being made by other technologies, such as the AstraZeneca virus, again, they are much more resistant to heat than the mRNA viruses. So what is in an RNA vaccine that I'm going to get injected? That's part of the myth, is that it contains chips, it contains 5G technology for internet. Those are not true. And we need to just move beyond that and not really look at, you know, something that is not evidence-based. There could be some fears based on some rumors, but really, I mean, when you really think about it, the composition is essentially 4 major material is in this. First is the RNA that I mentioned to you. And then there are a bunch of lipids in that vaccine. There are a bunch of salts, and there are some sugar elements. And the rest of them, other than the RNA, the rest of them are just helping the RNA to go inside your cell and also be stable. Because this RNA, when it goes inside your cell, that's another interesting to know, is that we are talking about, in some cases, 5-6 hours, then it's destroyed. It's not going to be there. It's not something that hangs around. There are also studies that says it could be, some of it could continue still being there in about days, but there, you know, it's not such a stable thing which is going to hang around your system for a long time. For this vaccination, we wish it would, but it's just not the reality. So let's take a look at when we say the clinical trials, we can trust the clinical trials, especially the phase 3, the advanced phases. I just wanted to show you one level of clinical trial. I believe this is the Pfizer trial. 45,000 people were injected and entered to the clinical trial, and from all different ages and all different genetic backgrounds and races. So when we see a vaccine like Pfizer or Moderna being effective 94-95% based on the clinical trial studies, those are really advanced and very expensive trials they did. They are not going to project something as, first of all, being effective, and second, being safe by a, you know, kind of like a limited study or something that is not done in an expansive and inclusive manner. So the studies they hold water. Now, if you were a scientist like me, and I just want to show you how boring it could get. This is like an example of the paper that I think Pfizer published in Nature. Nature is a fantastic journal, is a outstanding journal to publish. So what I'm trying to tell you is that papers after papers, they have to publish data. The other scientists look at it, they criticize it. And then this is all other than FDA looking at this data and asking the questions. For example, this, you can see the days that they injected and the titers of antibody that they generated. They need to provide really hardcore data and safety and everything. And things get scrutinized really, really strongly. So, fact, it takes time for our body to essentially generate a level of immunity that is going to be clinically relevant. So if you hear that, oh, so-and-so had the vaccine 2 days ago and he got COVID today, that's also expected because that person might have been exposed before vaccination to the virus and before vaccination to the agent, to the virus, and then he or she is getting the disease. It is also possible that the person was not exposed to the virus before vaccination, but he or she was exposed before the 2 weeks period that we could get some certainty in terms of immunity. and the infection goes on. Okay, so these cases have been out there, and there is a very valid scientific explanation of it. And that's why we have 2 doses of the virus. The overall understanding is that the first dose gives you about 50%, and the second dose, which is 20, 25 days away, is going to put you up around 94, 95%. So if you heard something like that, don't panic and don't be worried about it. It doesn't mean that the vaccine is not good. You could also experience some side effects such as fever. These symptoms are normal, and as immunity is being built up, some reactions inside your body is going to cause these side effects. But I encourage anybody who gets the vaccine to report the side effects to their healthcare provider, because it helps the manufacturer to have an eyes on the side effects. And when I got my shot at the VA Medical Center, they gave me a form, and I had a little bit soreness in my arm, and I reported that. And I'm hearing that the second shot will actually cause a little bit more of a side effects, and that's expected too, because now you have a level of immunity. The second shot is going to face your half-awake immunity. Therefore, there would be some side effects. I believe that's also normal. Okay, so now the question of the day, the myth of the day. Coronavirus vaccine can change my DNA because it's an RNA. RNA is the information material inside my cell. I have DNA, and this can go and change it somehow. Absolutely not true. As a matter of fact, it would be a dream for a gene therapist like me if I could inject RNA and convert the DNA, because imagine how many diseases we could fix this way. If we could inject the DNA, which essentially would go and make a new gene to get rid of thalassemia. If we could inject DNA and make a new gene, which would immune us against the cancer forever, integrate to our DNA, I'm going to be a transgenic human being. I'm not saying, I'm not saying that's something that I do in my lab. No, I told you I work on oncolytic viruses, but a lot of people for a long time were looking at something like that, and our human cells are incapable. For majority of the scientific data, they are not capable of taking the RNA vaccine from coronavirus and changing it to DNA. Therefore, that DNA could go and integrate to your DNA inside your cells. So let's take a look at here. Why is it not possible? First of all, location. The RNA that is going to be injected to you is going to stay inside the cytoplasm. Remember, the RNA that you're going to get injected is going to stay here. It cannot go back to the nucleus. Number two, even if the RNA was going back to the nucleus, we don't have any machinery to switch it to DNA and integrate it to our genome. Viruses can do that, such as HIV, the AIDS virus. They have that enzyme, they have that protein. They can bring the RNA, switch it back to DNA. Coronavirus doesn't have it, our cells don't have it. There is nothing out there which can help an RNA which was injected to your cells to essentially reverse back, become DNA. Because if you want to integrate to your DNA, you have to become DNA. Does not exist. In science, however, the academic way is that you can never say anything with 100% certainty, but you can say things with 99.9% certainty. And that's the number I want to give you. If this happens, the whole knowledge of biology and genetics that human beings have collected is almost wrong about this thing, which is, don't bet on it. So, and then stability, as I mentioned to you, it's that essentially RNA, which is going to be there, is only there for a short period of time, and then it's going to disappear. But during that short period of time, you're going to make those spike proteins, your immunity is going to become aware of it until you get your second dose. And then hypothetically, we are hoping that we will see an extended period of immunity against the virus. Okay. Now, at the VA Medical Center, I'm very glad and honored that I have received funding from the VA and Midwest Veterans Biomedical Research Foundation to start my research. My project is a little bit different from all of these things you heard. So we continuously told you that the technology so far is that we will make immune system in a way that immune system would go and does not let these spike proteins attack your cells. The strategy that I am pursuing is that when the virus comes inside, it will bring its own RNA, and that RNA starts commanding your cells to make viral proteins. I want to directly destroy this RNA. I want to get rid of that RNA. So there is no genetic viral material which is going to take over the cell and make it produce progeny viruses. So instead of giving the patient an RNA which is going to make a spike protein so immunity can go and destroy the virus, I am pursuing a strategy to right away kill the virus inside the cell, and it doesn't even let it replicate. And that's a gene therapy technique, which we don't want to get into, but I hope that at a later point, I could provide you with some information about our research. It's good to know that your own academic institutes at your own city are also pursuing this. And my strategy is not only a vaccination, but also a treatment, because if the cell is infected, we could probably help that. So, okay, now in terms of global efforts to vaccinate, let's see where we are right now. Let's take a look at where we are. This website is Our World in Data. It's a good website to take a look at where the vaccination is. I just wanted to bring it to your attention. You can browse it later. It gives you essentially per 100 people where the countries are. And you can see that, let's do to a better data if I could get that for you. So here, like number of COVID-19 vaccine doses administered per 100 people based on January 23rd. I looked at it, it was updated 30 minutes ago. So it's up to date. So as you can see, there are other countries which are ahead of us, but United States right now, it's 0.29 per 100 per people. It sounds disappointing, I know, but the fact is that we are a 300 million people country, and I am glad to see us up here. I didn't want to see us down here. So we are hearing that doses are being produced and are being distributed, and I will show you the distribution and the program that is for the state of Kansas and Johnson County. And I believe the majority of healthcare providers have received their shots, and now they are entering to other phases, including elderly citizens and public-facing employees. Meanwhile, it's important, obviously, to keep our defense up, keep our masks up until the shots are received. Once a good 60–70% of our population is vaccinated, we can put this pandemic behind us, and hopefully the world there is a group called COVAX, which is helping other countries, especially developing countries, to get their doses, and the humanity is going to be relieved from this nightmare. AstraZeneca, the one that is not making RNA virus, the company that's making the traditional virus, I read that in 2021, they will produce 3 billion doses. And they are AstraZeneca, I believe, is a British and Switzerland company with collaboration with the Indian manufacturers. And that is fantastic news. It's a traditional vaccine. The efficacy of it is 70–90%. So it seems like RNA viruses, based on the studies, are a little bit more active, efficacious. But if they could produce 3 billion doses and immediately deploy it, that's great news. And the schedules which allow 90% efficacy are extremely hopeful. And that vaccine does not need extremely cold conditions. So, and then let me, let's go back to our presentation. And one second, I'm sorry. We are about to be done. So And then let's see what else we got. Next, this is the vaccination plan for the state of Kansas. As you can see, I believe healthcare personnel, majority of them have essentially got the shots, and long-term care facility staff have also got the shots. You read in Shawnee Mission Post and Kansas City Star that on the Missouri side, they are also moving forward with public-facing first employees, first responders. I believe it is in the Kansas side too. So we are about here right now. We're about here, which again, availabilities as we go towards end of the winter and spring become more and more. I suggested about a week ago that Overland Park Convention Center would become prepared for as the vaccination site, because at some point, as I was being told very rightfully, at some point the vaccine is going to be available and we need a huge place to deploy the vaccine. I believe pharmacies are going to be involved. That's all good, but I think really our convention center, which is a facility built with tax money, is a great place to do that. I suggested that a week ago and to the city council and the mayor, and I'm waiting to hear back. Hopefully we could plan for that, because we can't be at the last minute and the spring is there and we have not prepared for this. Although the vaccination is in the hands of the state and the county, but I think at the city we could help and we could collaborate with them for sure. This is the site for the vaccination of the Johnson County. And I believe right now there is a calendar there. And if you go on this site, it's jocovaccine.setmore.com. If you go there, information is available there. I believe there is a level of information for people 80 years, I believe 80 years and older, that they could enter to a level of booking. So I encourage you to take a look at that and see what information is going to be there in terms of Johnson County's procedure to deploy upcoming vaccines. Let me see what else. This is about where I want to stop. We are in good shape. We are in a hopeful shape about the viruses. Let me knock on the door of the mutations that you hear as well. I believe I had a slide about it, at least. Let me just go back, see. So here, this line. There are conversations about mutated form of the virus. Now, as scientists, we have to be alert. We have to be, open our eyes to any possibility. If these mutations, if these genetic changes in these new forms of the virus, if they change that spike protein, obviously your vaccine has a potential to now not work, because your immunity is going to be facing a new spike protein. Your immunity, the vaccine that we are deploying, is going to make our immunity get used to and be prepared for the regular spike protein. So if the virus is now changed in a way that the spike protein changes, then it could be trouble. But there is no data on that yet. There are some concerns about the version of the virus mutated in South Africa, B-1-351. The one which is mutated in Britain, I believe the latest information says that that's not of big concern. It might transmit more, but the spike protein still vaccines are valid. This one they are focusing on right now to see if this mutation which happened in South Africa, if that is going to be something which our vaccines need to be adjusted. The good news is that both of the manufacturers, Pfizer and BioNTech, they say that their manufacturing line is very active, very versatile, so to speak, and they can change it if they need it, or a portion of the production, to now make a vaccine against the new spike protein. Otherwise, that mRNA code, they will change it in a way that when that enters to your body, it will make the new spike protein. Therefore, your immune system is going to be ready for that too. So we might be in a situation, there is a possibility that we would need to change the vaccine for maybe a part of the world because there is a certain mutation there. The mRNA technology, the greatness of it is that it is very fast and very versatile. So you could change it and produce a lot of vaccines in short amount of time. So, you know, for now, the vaccine is fantastic news. I'm not saying until this thing is worried, we have to be worried. Until this thing is over, we have to be worried about everything, but don't let the mutation news keep you from getting a vaccine or, you know, put too much pressure. We don't know a lot about them, but the manufacturing power is ready, the scientific power is ready, and they are working on it. I am gonna, number one, apologize if I spoke too much. And number two is that I'm gonna stop this and listen to you. So anything that you want to talk to each other or talk to me, I'm available. And the nightmare would be that none of us could hear me and nobody told me until now. I hope that's not the case. You could unmute yourselves. Anybody who wants to speak, go ahead and unmute yourself.
Doctor, I want to bring to your attention, my wife just took the second vaccine and she took it on Tuesday at 2 p.m. She worked at the inpatient pharmacy at the hospital. Now, she started getting fatigue at 4 o'clock that next morning. In the morning, she wake up shivering, sweating. She had fever, it was like 39 degrees Celsius. That went on all the way until early hours of Thursday. Thursday morning, she was fine. And she's still good. Thank God.
I'm glad. That's fantastic.
You know, I just got my second vaccine this week as well, and mine was the Moderna, and my colleagues as well, and we all were kind of going back and forth about our side effects, and very similar to that. Just a lot of fatigue, some chills. Some of us had fevers, rapid heart rate. So a lot of the typical kind of COVID type of symptoms that we see, but I think we've all recovered from it. So, you know, it went away fairly quickly, but we did find that there was more of an immune response to the second vaccine.
Excellent.
Yeah, my wife was, I think it was Pfizer, not Moderna.
Let me also thank Councilman Scott Hamblin from the city of Overland Park to be here and to participate in this conversation. I believe Councilman Hamblin also agrees with a potential preparedness to use the convention center for vaccine deployment if it comes to it.
Absolutely. Which I'll ask you a question while you're talking to me. I'll put you on the spot. So it was, I don't know, it might be maybe something I was watching on Netflix or something this week. Do you think, or in your opinion, they were talking about the possibility of, let's say you contracted COVID naturally, and maybe you had a weaker case of it. Did you still generate the same immune response, or could you have generated less of immune response, meaning that you're not as protected had you done the 2-dose vaccine, or does it make a difference?
If you do 1 dose?
No, if you had it naturally versus the 2-dose vaccine.
If you did it, so what I think is that, like I said, I'm not a clinician. I can give you a science-related answer, is that if you had a mild case of coronavirus, I think there is a chance that the titer of your antibodies is not going to be that high. Therefore, it clears from your system. But you would still have memory cells. Therefore, you would be better shape than somebody who has never seen this.
Right.
Now, where does that compare to somebody who had 1 dose of the virus? That I cannot answer without appropriate research. But we know that the recommendation right now, obviously, Scott, you know that even if you had COVID, if you were offered a vaccine, get it.
To still get it, right.
But if I got your question right. If one dose, we are comparing one dose versus a mild case, I don't have that much of an opinion.
No, I was comparing the people that you know, you got people that say, oh, I've already had it, so I'm good. But you know, I've read that's not necessarily true, because you could have had a weaker case and not had the immune response, where the vaccine is going to be broader and have a much bigger response. And
that's absolutely true. And influenza virus, every year we get a shot. And even if you get an influenza, it's not, nobody's going to tell you next year or later, don't get a vaccine. That's a mistake. The firm recommendation is to absolutely go ahead, and when it's offered to you, go ahead and get it. This is a completely different story. This is a controlled platform which with minimal side effects would give you maximum benefits. What else we got?
Hey, Ferris.
Yes.
Jerry Lewis, how you doing?
Good, Jerry. How are you doing?
Question. It's been reported on the news that we'll probably have to have a yearly vaccination and until we at least reached herd immunity throughout the world. That's what you're hearing?
That is what I'm hearing. That's what I'm hearing, and that's not bad news. I'm going to put a good spin on it, and I'm not constantly giving you good news, but the good news, Jerry, is that we might be in a situation that the mRNA technology would essentially provide one vaccine for flu, corona, and a couple of things in one shot. Because once you have these mRNAs, which are going to go inside and dictate a certain message, then in the same vaccine, scientifically and hypothetically could produce different mRNAs against different viruses. But yeah, I think that's very logical. For something like this, the way that our immunity has been acting, it could be a yearly shot. But you know, at that point, you are not really that much worried about it. The shot is available every year. They look at the mutation pattern of the coronavirus. That's what they do for influenza. Every year, they look at how much influenza mutated. And influenza mutates more than corona, by the way. And they will adjust the virus according to for the next year, according to the data that year. And the good thing, again, is that mRNA technology is so fast that maybe we don't need to be always 1 year late in terms of the way that we adjust our vaccine. Maybe we could adjust it for the very same year, essentially, based on the newest version. So that I agree with that prediction.
Thank you.
so I was going to say, talking about herd immunity, this is just another guess here. Clearly not a doctor. Is the herd immunity? You hear that as being a big number, and from what I understand, which could be completely off base, is because you get to a certain percentage, and like, from what I understand, like, well, you got the mutation, let's say in, well, I don't know, South America, but so as the virus goes wiping through an area, if it has no external pressures, you know, therefore it does not mute. It has less, which it really doesn't mutate much because it's got no external pressures to mutate.
The mechanism, Scott, the mechanism of mutation is simply virus replication and the machinery that replicates it miscoding it. So it is very much possible that in a limited geographic area, a mutation happens. So, and so therefore you don't necessarily need a huge population, but from the statistical point of view, the more number of people have this replication happening in their body, from the mathematical point of view, there is more chances for a misread. You know what I'm trying to say?
Right, yeah.
If you have 200 students in your class, there is much better chances that 5 of them would do the homework wrong rather than 20 students, just statistically. But even in, even in a limited area, I mean, limited geographic area, as long as the virus inside somebody's body is replicating, there is a possibility for mutation. But what we know is that DNA viruses, herpes virus is the king of stability. the genome of this virus almost has not changed during probably millions of years. RNA viruses are less stable. So when the herd immunity, which means that 70% of the population have been infected either by the vaccine, and has immunity, either by the vaccine or by the natural disease. When we are at that point, even if a mutation happened and we are facing a new situation, I think we are still in way much better shape.
Well, and that's the point I was getting to is, so a mutation happens. If you're at 70, 80% immunity, then it has less of a chance to find another live host and continue to multiply. Is
right. Right. The influenza virus, the perfect example, mutates every year on us, mutates every year, and we adjust it. But what I'm saying is that from the clinical, I think, again, I wish we had a little bit more information on the mutated forms, which we don't, but like you say, as the herd immunity is deployed, impact of the mutation would become much less as well, because your system is not overwhelmed. Your capacity to deal with it is there, and you can even simply redirect your manufacturing line to get a vaccine going for that mutated form. What else we got? Anything else? Anybody who's, I mean, if you thought that something I said was incorrect or any point of view against it is completely welcome. We are just having an open conversation.
I see there's some chats down there.
Read them, Scott. Let's see what we can say.
Okay, this one says, will immunizations cause the virus to mutate? Now that immunizations are occurring, how long will a mask wearing need to continue? If you mentioned that, I'm sorry, I had trouble staying logged in and had to log back on. But I've heard the same discussion on how long the mask thing will continue, because I've heard opinions once we hit a certain point, then it's just we're back to like the flu, and there is no point for masks.
They say, I heard from good resources, again, that's a mostly clinical conversation, when we don't have people dying from coronavirus, or it's very low number of people dying from coronavirus, that's when we can stop wearing masks. I think that's a logical indicator. Yeah. I think that's a logical indicator, which I think it's a year. I think it's by the end of this year, but I think it's a logical way of thinking. Nobody can, tell you exactly by this time you're not going to wear masks, but when the death from coronavirus, hospitalization from coronavirus is significantly low, very low, maybe at the level of influenza, you don't wear masks that much. Although we know that many nations around this globe, they always wore masks. Even when we were not wearing masks, they wore masks. But I think when it gets to something like influenza or less than that, hopefully with this new technology, I think that at that point one could think about putting the masks away. But until that point, we need to protect ourselves. That's what I think. Anything else we got there? I was not looking at. All right.
I'll throw one more at you.
Sure, please.
So you hear on the news, and I know they're looking for what's the term I'm looking for? They're looking for sensational news, talking about people having a major reaction. The media's out there searching for somebody that has a major reaction, but I mean, there's people out there now that are allergic to certain vaccines, right?
Correct. Yeah.
Yeah. So if this was the flu for the first time and everybody in the United States or on the planet was going to get a flu vaccine, we'd hit an absolute significant amount of reactions on that too, right?
Absolutely. Undoubtedly.
So, yeah.
Undoubtedly.
It just so.
And I showed you what is in the vaccine, that slide, and compared to an old school vaccine, these RNA vaccines are actually much more pure with less additives. You know how it was in one of the movies, it was telling you that in order to make the vaccine work, they have to add adjuvants. They had to add additional things. these mRNA vaccines are the mRNA itself, which is very, very low, possibility of allergy. Then you got bunch of salts, you got bunch of lipids, and you got some sugar there. And if anything, the chance of having, in my opinion, having an allergic reaction to such a pure composition of 10, 12, 20 chemicals is much less than a vaccine that is produced by, thousands of things together. Yeah, it's very simplistic to think about it like that, but you're absolutely right. If was the first time, you just said it perfectly, that we were deploying influenza vaccine, then we would be having some people having significant reaction to it too. And we still do have that. I'm sure we all have heard somebody got a vaccine and it didn't treat him well.
Yeah.
Quite natural for that. In medicine and pharmacy and drug development, you always have a balance of side effects versus benefits. You look at the chemotherapy drugs, what terrible side effects, but still you deploy it because the benefits is much more than that. So I think it's good to know about side effects, but focusing on it and expanding it and essentially making it out of proportion, we have to stay away from that. I appreciate everybody who was here. Thank you very much. And it was a great pleasure. Councilman, thank you very much for your questions. Thank you for the I wasn't paying attention to the chats. Everybody who was here, thank you very much. I wish you the best of health, the best of,
Dr. Thank you for your effort. I wish you put it on YouTube. This lecture is very.
I'll do it. Councilman Hambling controls our conversation series.
Oh, yes, so I can do that.
Put it up there. I appreciate it. We consider this a conversation series, and we will hopefully we'll provide updates about as things move on. And if you guys had any suggestions, anything that you think we could do, and as City of Overland Park, Scott Hamblin, Faris Farasadi, please send us an email. Please let us know, and I wish you the best of luck. Thank you. Bye-bye, everybody. Thanks.